I'm just going to say this and process it. It's pretty simple. Plane z equals c, 4xy equals c squared, right? Well, that means, of course, if z equals c, since z squared equals 4xy, that means 4xy equals c squared. Okay? And again, that's something that can't happen in the fourth and second quadrants because 4xy will be negative. It can't equal the square of anything. Just to reinforce that idea. Well, this just tells us then that y equals c squared over (4x). Okay? And I want to write that as c squared over 4 times 1 over x. Because we know what the graph of y equals 1 over x is, and this is just a vertical stretch of that graph, right? Again, reinforcing what you guys who are all pre-calculus tutors, okay, would need to be telling people about how to construct this graph. We don't construct the graphs by going to a graphing calculator and pretending we understand what we did. Although in some pre-calculus classes I'm sure that happens, but probably not on this campus. Okay? And hopefully not in any of our courses. Fine to use a graphing calculator if you know what you're looking at. Or if you use a graphing calculator, then explain why the output is what it is. That's sort of valid, but you need to be able to construct. Okay, well anyhow. Because when you get to this course, you don't want to be messing with the graphing calculator to visualize this. You'll be punching buttons all day. Okay? So, what is this? It's a vertical stretch by factor c squared of the y equals 1 over x function. So we have this whole function family, which I'll just graph in the first quadrant. But what happens in the third quadrant is just symmetric with this, or anti-symmetric, you can figure out which. Symmetric about the origin, what it is. Well, here's a graph of 1 over x. You got the point 1, 1 here. Right? Well, if c equals 1, well then you have 1/4 of this, right? So every point on this graph moves 4 times as close to the origin. So this point's going to move down to here, this point's going to move down to here, this point's going to move down really close to the origin. So you're going to have a graph that looks something like maybe this. Okay? So this is for c equals 1. For c equals 2, well, c squared over 4 is 1, so you just have your 1 over x graph. For c equals 3, you've got 9/4, which is a little over 2, right? 2 1/4. So every point moves a little more than twice as much higher. So this point might move up to about here, and this point might move up to about here. So your graph looks something like this. C equals 3. Okay? Now where's c equals 4 going to be?
Even higher.
Yeah, is it how are these things going to be spaced? Is this going to be closer to this? Or is this going to, which two are closer, these two or these two? That depends on how you measure closeness, but let's just measure it along this line where y equals x, right? Okay, if y equals x, you know you have here the point 1 1/4 here. But along this line where y equals x, what do you have? Well, you can think about that, okay? Where does each graph intersect the line y equals x? So what are these points? Okay? It's a profitable thing to look at, as well as what I'm showing you about the vertical stretch, okay? But it's going to turn out that, well, c squared gets bigger faster and faster as c keeps increasing by 1, right? Like, you go to c equals 4, and you get 16 over 4, which is 4, right? So c equals 4 is going to be a little further out, right? c equals 5 is going to be even further out. So these things are going to space further and further apart. So not trying to draw this all that accurately, but you're going to have graphs that kind of do this sort of thing. Gets a little further, goes a little further, goes a little further, right? So this might be c equals 1, c equals 2, c equals 3, c equals 4, c equals 5. Okay? Now what is c? Well, z is c, right? Which means that now if you want to do this in 3 dimensions, you just come up 1 unit above this, 2 units above this, 3 units above this. So the graph is this high here, then this high here, then higher here. So the graph is going up like this, but it's got a downward curvature because z just changes by 1 between any 2 of these contours, right? Okay? And these contours are further and further apart. Okay? So z increases, but it increases at a decreasing rate because the intervals in the xy plane over which it increases get bigger. Okay? And you might want to process that statement.